Hello, everyone. Welcome to this webinar. I'm Damien Wiley. I lead product for Wherobots. I'm joined by Will Lyon, who leads developer relations. I'm also joined by the engineers that built the new capabilities we will talk about today. Ryan Avery is a lead developer on raster inference, which makes it easy to derive insights from satellite imagery at scale. James Willis led the development of V-tiles, which cuts vector tiles faster with higher scale and lower cost than any solution we know of. And Peter Folds led the development of the Spatial SQL API, which broadens the utility of WherobotsDB, our spatial compute engine. So let's get into the agenda here. Excuse me. So before we dive into the new capabilities that we just released, we want to give you an overview of Wherobots as well, to discuss why Wherobots exists in the first place, to give you a sense of our mission and the realm in which we're innovating in. We'll also be sharing and demonstrating the new capabilities that we recently launched for Wherobots Cloud. And finally, after we demo these capabilities, we'll leave you approximately 15 minutes for Q&A. And we look forward for an open and discussion with the folks that built these capabilities. Let's discuss a few inconvenient truths. The rate of change in our physical world will only accelerate, and this change is already affecting you. Change is everywhere. Populations are growing and moving. Your customer demands shift in a single tweet. The resources your business depends on are in flux as a result of warfare, climate change, natural disasters, or change in harvests. There's a never-ending tug of war between weather and road conditions, and your operations and logistical plans. Real estate opportunities come and go as fast as a lightning strike. These are all forms of spatial problems. But if I were to ask you, is your organization capable of making data-driven decisions to continually solve these spatial challenges? I'd wager most of you would say, no, we are not. Here are a few other inconvenient truths. Building and running geospatial solutions today requires expertise that you may not have in-house. This is because geospatial data almost always needs one or more rounds of transformations to be useful, and most geospatial solutions are built by stitching together multiple suboptimal components to build a solution, which also involves unique workarounds. And the talent you probably have in your site inside your company may not be experienced with creating and running these types of architectures, let alone they may not need to be. The scope of the problems customers want to solve are geographically vast, complex, and involve large to planetary scale data sets. The solutions that exist today do not scale, or when they scale, they don't perform. There are old guard geospatial vendors that lock you into their old guard solutions, stifling your innovation and recharging these challenges previously mentioned. This means you need to maintain and migrate copies of data, and all the curated data sets you depend on are locked in, all of which increase your costs and the pace in which these vendors funnel in your money. Finally, modern big data solutions like Apache Spark, Databricks, Snowflake, and Amazon EMR aren't optimized for geospatial. For these vendors, geospatial is treated like a side project, and you can see this in the support that they provide you today. The reality is that geospatial hasn't been given enough love within and around the computational layer in the cloud. We're changing that. Wherobots was started by the original creators of Apache Sedona, and we specialize in geospatial in the cloud so you don't have to. First, Wherobots gives your teams the ability to analyze raster, vector, structured, and private and open data in one place on a performant and scalable cloud solution. giving your team superpowers that cannot be found elsewhere. The Wherobots products are all designed to support data sets of any scale, including planetary scale. This eliminates the need for you to develop workarounds such as geographic partitioning or addressing vertical scale limitations in your architecture. Wherobots embraces the open data architecture by utilizing your data lake as its storage layer in an open storage format. That way, you can deploy the best solutions to your data over time without having to worry about your data being locked in. Our product experiences in serverless spatial compute engine are purpose-built to deliver up to 60 times better performance than what is otherwise considered modern big data engine. The truth is, at Wherobots, geospatial is all we do, and we do it really well. This all started with Apache Sedona. Wherobots founders, Mo and Gio, were the original creators of Apache Sedona, and Wherobots is built on and compatible with it. Apache Sedona is an open source solution that brings modern geospatial capabilities to Apache Spark. It's widely adopted across industry sectors and is used extensively with Amazon EMR, Databricks, and Snowflake, among others. The reason it's widely adopted is it supercharges Spark with these geospatial capabilities that Spark doesn't have. Apache Spark's big data and distributed capabilities are a great fit with Apache Sedona's geospatial capabilities because it makes it easy for users to address large-scale geospatial ETL and analytics problems. And this is why you see organizations like Amazon, Uber, and JP Morgan Chase deploy Apache Sedona on their data lakes and lakehouses, because each of them have significant geospatial challenges to solve, and they found Apache Sedona provides the best solution to their problems in open source. While Apache Sedona has significant traction in large organizations, it's gaining traction broadly. Apache Sedona's community and usage is growing rapidly. We're pleased to share that Apache Sedona has more than 30 million downloads a month, and it's growing rapidly and at a rate of over 130% growth year over year, and is supported by over 120 contributors. Apache Sedona is the best open source option for distributed geospatial computing, but at Wherobots, we take the benefits of Apache Sedona to another level, and here are a few of them. First, Wherobots is compatible with Apache Sedona, but we've implemented customizations under the hood that make it more than 10 times more performant than Apache Sedona on its own. This means you can lift and shift your existing solutions based on Apache Sedona into Wherobots and reap immediate performance and productivity benefits. You don't need to configure, provision, or manage compute. We do all of the heavy lifting for you, which again amplifies this productivity gains that you can reap using Wherobots. Wherobots scales compute horizontally, which lowers overall cost compared to solutions that vertically scale. It's designed to maximize productivity at any scale, which means you can forget about all the workarounds you built to deal with limitations of previous solutions. It's also open and cloud native. As I mentioned, Wherobots is built on Apache Sedona, but it's also built on top of the open data architecture so that you can have the assurance of being able to run these new solutions over time on the data that you make control of. It's also cloud native. Currently, we're built on AWS, but we do have plans to bring Wherobots to Azure and GCP as well. We offer a spatial catalog that provides you the ability to analyze data across the Wherobots, across the data sets that Wherobots is integrated into. So for example, you have out of the box, you have Overture, Landsat, and OpenStreetMaps data sets that you can use to join with data sets that are in Amazon S3 to build these curated tables, spatial tables that are meaningful for you and your business. And then finally, we've built and will continue to develop AI and ML capabilities that you can leverage out of the box that would otherwise require significant expertise and development with Apache Sedona to accelerate your end use cases. Let's dig into some of the performance benefits. What this slide shows you is significant proof that we do geospatial really well. We benchmarked Wherobots DB against the modern big data solutions using joins, which are described below and you can run on your own. The joins are straightforward and utilize the ST-intersects function along with the Overture and OpenStreetMaps datasets. The key takeaway here is if you look across the different solutions, is that if you already have a geospatial ETL analytics workload running outside of Wherobots, it's very likely to benefit from performance gains if it were running in Wherobots. And if you're considering Wherobots for new workloads, you're most likely starting with the most performance solution out of the box. And in terms of benefits, you can see that Wherobots, relatively speaking, it varies based on query, but it can deliver significant performance gains, even over 100x, depending on the query and the alternative solution that you're considering. Let's talk about a couple of the common use cases that our customers are using Wherobots for. First is geospatial product development, and this ends up powering all of the use cases that we'll talk about next, along with the ones that are not. Geospatial product development is the production process required to build geospatially enabled data sets ready for analytics or other end use. We're working with a number of insurance companies along with companies who need to analyze real estate risk at scale. These companies are building new products and making better investment decisions because Wherobots is arming them to make data-driven decisions about their assets or investment options in the physical world. GPS data is commonly the basis for insights and telematics use cases. Fleet logistics and operations, along with user-based insurance products, rely on analyzing GPS data at a very high scale, and these customers use Wherobots in their analytics pipelines to make sense of their GPS data. And then we have customers using Wherobots to perform aerial analytics, such as change detection on satellite imagery, from the standpoint of SQL or Python. Insurance, risk managers, and urban planning managers can utilize Wherobots to derive insights from satellite imagery at any scale. We'll talk more about this use case in a little bit later in more detail. Here's an overview of the product architecture at Wherobots. So at the lowest level is the spatial catalog, which gives you a single pane of glass for discovering, joining, and analyze data sets from the open domain to data sets that are proprietary to you in different storage systems. And by default, the curated data sets that you create in Wherobots are stored in your Amazon S3 bucket in an iceberg table formatted as GeoParquet. Out of the box, the spatial catalog provides you with access to the most popular open data sets from Overture, OpenStreetMaps, and Landsat. Wherobots DB is our spatially optimized compute engine, and Wherobots AI, which we'll dive into shortly, utilizes AI and ML to make it much easier for you to extract insights from aerial imagery and GPS data. Each of these work directly with the spatial catalog. We currently support 3 interfaces for Wherobots DB and Wherobots AI. First, there's a managed Jupyter notebook environment that contains a number of example notebooks to get you started developing using SQL and Python. Once you're ready to take your code to production, we have a jobs product that can automate the creation of your data products. And then we have a Spatial SQL API that broadens the interfaces you can use with Wherobots. We'll talk more about the Spatial SQL API shortly. All right, let's dig into the first feature that we released a few weeks ago, Wherobots AI Raster Inference. It is a new capability that makes it really easy for you to analyze features of interest in satellite imagery on a planetary scale. Here's how it works. It starts with satellite or aerial imagery in GeoTIFF format on cloud storage. Imagery can come from a variety of different sensors suitable for vegetation monitoring, urban areas, oceans, etc. These GeoTIFF datasets can be loaded into Wherobots using SQL or Python. They take the form of a raster table within Wherobots, and then from here, raster inference makes it efficient and easy to run different detection functions, such as segment, classify, and detect. In this example, we have a georeference prediction of a solar farm derived just from satellite imagery. These predictions can be represented as a table in Wherobots, which this table is then interoperable within the Wherobots ecosystem, so that you can say take other tables and join them to enrich the insights that you derived from the satellite imagery. So here are a few use cases that raster inference is good for. In any situation, there's signals and object of interest, and those signals or objects of interest are something that you want to analyze using raster inference. Raster inference scales the ML models and automates the detection and analysis of what's happening in the imagery. The results from the raster inference can serve as inputs for catastrophic risk assessment, such as mapping landslides or historical flooding to inform future forecasts of hazardous events. You can also utilize raster inference for damage estimation. For example, before and after a weather event, you can use it to detect how widespread damage was in an area of interest. And then there's also the use case of using raster inference to measure environmental and infrastructure change, which you could use, for example, running a before and after on different satellite images across different dates to predict results and measure the change. So open source AI models power raster inference, and we currently support detection of solar farms, marine infrastructure, and land cover. And we plan to support more use cases over time, and we look forward for your feedback. These models can be invoked from SQL or Python, but soon we will support the ability to bring your own model into raster inference so you can utilize this feature with models that were customized for a specific use. Raster inference makes it easy to georeference model predictions, control the quality of predictions, and join these results with other large geospatial datasets. That means you have the ability to analyze raster, vector, and structured datasets in one place. You don't need solutions for each of them. You have one now. Finally, like the rest of Wherobots, raster inference is serverless and pay-for-use, which lowers costs and streamlines time to insight compared to doing this yourself. Wherobots AI also offers a map matching capability that you can use in your telematics data pipelines to improve the quality of your GPS data. It leverages a Wherobots optimized model to snap noisy GPS data points to transportation segments. Because GPS data is inherently noisy, in order to make sense of it, you need to have a high confidence that GPS data point was associated with a path taken. And what Wherobots AI map matching does is it takes the noisy GPS data points and then snaps it to the most likely road segment that device was associated with. And most importantly, it's capable of doing this at a very, very high scale. You can match millions of points per minute, and it also is at a very, very low cost. Here's a quote from a customer of ours who's used map matching and is a leading telematics solution provider. They use Wherobots and Wherobots map matching to make sense of hundreds of billions of vehicle trips, which creates insights that were otherwise out of reach while lowering the cost of their pipeline by more than $800,000 a year. Let's talk about the Spatial SQL API. And what it does is it broadens the utility of Wherobots. We also built it with an integration with Apache Airflow to make it easy for you to automate production jobs in Wherobots. This API, we started with SQL, but we also will support a Python API soon. So what you can think, the way you think about the spatial SQL APIs is that it allows you to tap into the power of Wherobots remotely. So and we also built a JDBC driver along with a Python DB API so that you can integrate other SQL IDEs with Wherobots. Vector tiles are utilized in modern map applications, and they can dramatically improve map interactivity and understanding for the end users. For example, you can probably see them in action when you see buildings overlaid on a map, maybe in your car, on its mapping interface or online. And we found that the capabilities for developing vector tiles, they lack scale, they were inefficient, they were hard to develop with, and they were costly. We addressed all of these challenges with vtiles for Wherobots. Vtiles is a Wherobots DB feature that makes it very easy for you to generate vector tiles in the modern PM tiles format efficiently and at any practical scale. Let's see how it performs. So we generated vector tiles in the PM tiles format for the entire Overture buildings and transportation segments datasets. This represents roughly 1 billion features worldwide, and we utilized and we built the vector tiles utilizing zooms across zoom levels 4 to 15. We did this on a Tokyo runtime, Wherobots Tokyo runtime, and this operation took 23 minutes to complete at a cost of approximately $150. We think that's pretty fast and efficient for a planetary scale operation. All right, so let's get into I'm going to transition the mic over to Will, who will now demonstrate these products in action. Will, take it away.
Great. Thanks, Damien. Let me go ahead and share my screen here. Okay, and give a holler if you're not seeing my screen, or if you're seeing something different here. But we are signed into Wherobots Cloud. So this is the main dashboard page for Wherobots Cloud if you haven't seen that before. And by the way, anyone can sign in and create an account for free at Wherobots Cloud and try out all the things that we're talking about today. So I've started a notebook runtime, and what this looks like is a hosted Jupyter environment in Wherobots Cloud. And what we're going to do here, let me zoom in a little bit, make this as big as we can here. So what we're going to look at today is a demo that we put together that tries to highlight the 3 main new features that Damien talked about today, which is raster inference, so running query time inference on aerial and satellite imagery, the Spatial SQL API for integrating the results of our analysis with other systems, and generating vector tiles. And so the example we're going to look at today is a site selection or suitability analysis, trying to answer the question of where should we build new electric vehicle charging stations. And there are going to be 3 inputs into this analysis. The first is identifying existing EV charging infrastructure. So where do we have supply of existing EV chargers? And the second one, second piece of input is going to be proximity to retail stores as a proxy for demand of EV charging stations. And then the third piece of this is we want to understand our access to and supply of solar energy. And so that's what we're going to use raster inference for to identify solar farms because we want to make sure that our EV chargers have access to solar energy. So this is the first piece of configuration here that we're running in the notebook. If you've used Wherobots Cloud, this should be familiar to. We're configuring some access to S3 buckets and some configuration for our runtime. The first piece we're going to do is identify our area of interest. So we're interested in the state of Arizona. So that's going to be the focus for our analysis, and our level of aggregation is going to be at the zip code tabulated area level. So we're using some data from the Wherobots Open Data Catalog to identify the boundary of Arizona, and then data from the Overture Maps table within Wherobots Open Data Catalog to identify the US Census zip code tabulated areas. So here's our area of interest. And what we want to do is essentially prioritize each of these zip code levels to identify where are good opportunities for EV chargers. So the first piece is going to be bringing in existing EV charging infrastructure. So we're loading data from OpenChargeMap, which is a public data set of existing EV charging stations throughout the world. We're loading that in GeoParquet format. And then here we're just visualizing a sample of the data using Kepler GL, which is an integration for visualizing data from Wherobots. So now what we're going to do is basically do a group by using this st-intersects predicate to identify charging stations within each zip code. And that gives us a count, so a spatial join here, where we're joining these two tables and getting a count so we can see some measure of the availability of EV stations. The next piece is our demand proxy, which is pulling in retail stores. So we're filtering the entire Overture Maps Places data set here to identify within our area of interest. So within each of our zip code areas, identifying retail, grocery store, and restaurants, getting a count of those within each zip code as well. So now we have some proxy for demand, some rough information on mobility data, how many folks are driving around in these areas. And then to combine these two measures of the existing EV chargers and retail stores as our proxy, we're going to normalize both of those on a scale of 0 to 1 to come up with this opportunity score. So if the opportunity score is 1, that represents where there's the biggest opportunity for building new EV chargers in each of these zip codes. And for the third piece here, which is going to be identifying our supply of solar energy, we're going to take advantage of the raster inference functionality in Wherobots AI, which Ryan is going to talk us through.
Hey, everybody. So yeah, now that we have our demand side of the equation sorted out with proximity to retail stores and existing EV charging stations, let's use satellite imagery to map features that we don't already know the location of. We don't already have a data set for solar farms. We want to site these EV charging stations where there's sustainable energy sources. So to do that, we want to map solar farms. So to this end, we've prepared a Hapsu raster table containing our Sentinel-2 satellite imagery. This is 13-band multispectral imagery with 4 time steps for each sample. So we're going to load this in with Sedona.table. And we can take a look at what is being described here. Each row represents an individual Sentinel-2 tile, 1024 by 1024 pixels. So we've prepared all of this with the RS functions available in Wherobots DB. Each Sentinel-2 tile has a geometry. We can use this geometry to constrain where we run raster inference. We can also filter by start date time and end date time if we only care about running inference over certain time periods. And we have this outDB raster object that represents the actual Sentinel-2 tile raster. It has all of the geospatial coordinate information, the bounds of the raster, and also a reference to the actual data. So we'll be using this to run raster inference. So if you scroll down a bit, we'll first use the geometry that comes from that outDB raster object to join it to our Arizona zip code geometries. So we'll use st-intersects in this SQL statement here to make sure that we're only running inference for zip codes and that we care about in Arizona. We'll also constrain this inference to where we have a demand opportunity score above 0.9 and where the scenes that we have were acquired after October 1st of 2023, just so that this demo runs on like relatively fast. And you can try this out yourself in a GPU runtime on Wherobots Cloud. So here, we're going to count how many scenes we have to run on. I think this is about a couple of thousand scenes, about 85 gigabytes of imagery. And yeah, it looks like it's 3,000 scenes to be exact. And the next statement we run is running raster inference. So there are 3 detection functions available in raster inference: classification, object detection, and segmentation. Segmentation gives each pixel a classification. So we want to map the pixels in our satellite imagery that have the solar farm class. So we're going to use RS segment to accomplish that. And we're going to supply a model ID that points to a model we've integrated into Wherobots Cloud. This is a model from a project called Satlas, which released many open source models fine-tuned for different detection use cases. And so we'll use a model that's been tuned to detect solar farms. And the next argument to RS segment is our outDB raster column, which points to all the imagery that we want to run inference on in our table. So with that, we're running inference. So in the next cell, we'll just unpack the resulting fields from the inference result. And this takes about 6 minutes for quite a lot of imagery, almost 100 gigs of imagery, 3,000 scenes. And the result we get is, as I said before, with segmentation, every pixel gets a confidence score. So we have a confidence array, and this needs to be geolocated. We need to assign geospatial coordinates to this so that we can join this inference result with other data sets. We also want to vectorize it so that we can join this with other geometry data sets. So for this, we'll use RS segment to geoms to convert this confidence array, where every pixel gets a confidence score, to a vector. So we're going to supply our outDB raster column. We're going to supply that confidence array and a confidence score threshold. So next, once we have our geo-referenced predictions, then we need to also consider that many scenes that we run inference on are not going to have the features of interest. They're not going to contain solar farms. So we want to filter out these empty geometries, these scenes where no predictions occurred. And to do that, we'll use st_is_empty. So with that, we have 132 scenes that were detected to have solar farm locations. So if we scroll down, we can see that we now have a table with our geometries, and we can plot these right away with Stone and Kepler. And so here, Will has already plotted and zoomed in on some example solar farms. I encourage you to check out this notebook yourself, run it in a Wherobots GPU runtime, and check out how this model performs. You'll note that like the imagery we're using as a base map comes from a general Mapbox base map. So we're not visualizing the source imagery that was used by the model. This is on the roadmap to make really seamless and snappy. But you can see that in many cases, the comparisons match up, which is encouraging. So with that, I'll throw it back to Will to talk about how we're going to compute our final suitability score.
Cool. So we have the three pieces to the input of our analysis here, and our final suitability score. What we're going to do is normalize some measure of the area of the total solar farms detected within each zip code area and normalize that on a scale from 0 to 1. So we're calculating the area from our predictions polygons of predicted solar farms and normalizing that from 0 to 1. So a score of 1, those are the zip codes with the most area of solar farms detected. And then we're combining that simply linearly with our opportunity score. So if we have a score of 0 to 2, where 2 represents the highest possible score for assigning which zip codes we want to build our new EV chargers in. And we can visualize that in sort of a choropleth in Sedona Kepler. And we can also kind of verify here if we take a look at all of the inputs into our analysis here, which we can visualize together. So here we can see the polygons of the detected solar farms. We can see existing EV charging stations. We can see existing retail stores within each of our scored zip code areas. So the next piece is how are we going to share this analysis? This is part of our data pipeline, but of course there's further analysis that we want to perform on this data. And one of the ways that we can do that is to write the results as PM tiles. So Damien talked about how we can generate vector tiles using Wherobots V tiles. And essentially to do this, we can assign multiple layers from one or more data frames and write these tiles to, in this case, the S3 cloud storage that comes with our Wherobots cloud account. So here we're creating 4 different vector tiles, and we can then visualize those. So we have vector tile, PM tile for each of our inputs, the 3 inputs into our analysis, and then 1 for the final results. We could also do this as a single PM tiles file with 4 different layers, just kind of different options there. We can visualize those in the notebook. We can style those using vector styling here and kind of visualize the results, which this looks similar to the data we were seeing before. This is the sort of final results of our suitability analysis plus the inputs into our analysis. So PM tiles are good for visualization in sort of web maps. And if we want to sort of get a quick look at the data for sharing with colleagues, but of course we could also write the results of our analysis to the Wherobots Spatial Catalog, another feature that Damien talked us through that is based on Apache Iceberg. And so the idea here is that rather than saving individual files and having to think about how do I deal with Parquet files, GeoJSON files, this sort of thing, that we have familiar SQL tables to work with that support native geometry types and spatial operations. And so what we're doing here is creating a new table in our Wherobots catalog, suitability EV chargers. And then we're going to write the results to this table. So we're writing the final score, the zip code, and then the polygon geometry to our table here, which we can then share with other users throughout our organization. Another option, though, is we might want to access this data in an external system. And so Damien talked about the Spatial SQL API and the database drivers, both in Python and Java. that are now available. So one example here might be we want to pull the results of our analysis into a tool like QGIS, which is a desktop GIS tool. Perhaps we have some existing workflow with our analysts who are using tools in QGIS to create visualizations or further analysis. And we want to be able to integrate with those sorts of toolings from Wherobots. So in this example, we're going to install the Wherobots Python DB API. This is the package for the Wherobots Python driver. And this Python code, we're going to run in QGIS to load data from this table that we created up above, the Wherobots Suitability EV Charger. So that's this table here, this data that we created, and then create a layer in QGIS. If I switch over to QGIS, here's the Python console. So this is the same code that we saw in that notebook. We are creating a connection. The way this works in Wherobots Cloud, we create an API key, and then that's our access token for accessing data that we've stored. And we can create a runtime in Wherobots Cloud as well. Here we're just executing a very simple query. So we're just selecting all the rows from this table. We could also take advantage of the scalability functionality in Wherobots to run more advanced spatial operations here, converting that to a geodata frame and creating a new layer in our QGIS project. And then we're visualizing the results in a simple choropleth here, but of course we can continue on with further analysis within our QGIS workflow. Cool. So that's an example that just shows how we can apply a lot of the tools and techniques available in Wherobots that we talked about earlier to a suitability analysis project. This went through this kind of fast. The code for this is available on GitHub, which I think we shared in the chat. We'll share that in the chat and send this out as well for folks in a follow-up email. Great. Well, with that, let's take some questions from the audience here. I think that feel free to ask questions in the chat. We have engineers from the team who have built these features. So if you have specific questions about some of the functionality we talked about today, feel free to ask those specific questions. So let me kick us off here. I'll take a look in the chat as questions are coming in. So I see a question here that says, Wherobots cloud native application, is it suitable for edge computing? For example, it can be integrated with local applications. Does anyone want to take that question?
I mean, I think that if you take the question very literally, the answer is no, right? Wherobots runs in the cloud. I have some experience with open source Sedona in a previous job outside of Wherobots, where we were doing edge processing, and then the results of the edge processing were made available in the cloud, and we did more advanced processing using Sedona in the cloud. So maybe not a direct answer, but that's a pattern I've used in the past to access the power of Sedona on a project that was primarily using edge compute to gather data.
Cool. Thanks, James. Yeah, and I think with the availability now of the Spatial SQL API with the Python and Java drivers, that allows us to execute queries against Wherobots in those sorts of environments. Great. So another question here. This pertains specifically, I guess, to raster inference. So could you speak more about the different types of inference supported? You mentioned segmentation, classification, detection. Are there different types of problems or use cases that these different types of inference are geared towards? I guess that would be a question for Ryan here.
Yeah, hello. Correct. Yeah, those are the supported inference types, and they're suited for different kinds of applications. RS segment, which provides a classification score and classification label per pixel, is more suited for applications where you care about the exact area, measuring area of a feature of interest, and delineating the exact boundaries of a feature of interest. So, for example, if you're interested in mapping clear-cut forests in the Amazon, and you want to know not just roughly where those clear-cut forests are, but exactly how much area has been clear-cut, RS segment would be a great use case for that. RS B-box detect for object detection is really good when you want to count features of interest and localize them. So maybe you don't care about measuring the area of marine ships in the ocean, but you want to count marine ships and localize them. Object detection is really good for that. And then RS classify, that's good for whole scene classification, where you want to maybe approximately localize features of interest just to the geospatial coordinates of the scene as a whole. So we provide an example that shows classifying land cover in Sentinel-2 imagery. And so RS classify is great for that. How they all fit together. In the past, I've used classification models to filter satellite image scenes because classification models are cheaper to run. And so we'll do a first pass of classification to filter where we want to run more expensive models like object detection or segmentation models. That's one example. And yeah, happy to talk about more applications if you have follow-up questions.
Great. Thanks for that, Ryan. Yeah, and as Ben said, we've enabled microphones from folks. So if anyone wants to ask a question verbally, just use the raise your hand feature and you can ask that verbally, or if not, feel free to keep dropping questions in the Q&A form or in the chat, and we'll be sure to get to those. I saw Thomas, you had your hand raised at one point here. Did you want to ask your question verbally, or feel free to go ahead? If not, no worries. We can come back to you. So a follow-up question on raster inference, which Ryan was just speaking about with different types of inference supported, the segmentation, classification, object detection. Is there a limit or restriction to the type of models that can run in Wherobots AI? How do we know if a model is supported by Wherobots? Oh, and Ryan, I think you're muted.
Oopsie daisy, thank you. Yeah, so the current models that are supported conform to a specification that we've been working on since early this year to describe how to run models on spatiotemporal datasets. If folks are familiar with the spatiotemporal asset catalog extension stack, this is a stack extension to describe how to run machine learning models, not just on our platform, but just in general. So we're describing our models with this extension. So if your model is also described with this extension, that enables compatibility with our platform. I can talk to you more about this. This is a feature that we're going to be releasing in the future, like bringing your own model. So we're definitely looking for folks that are willing to try this out. So yeah, if that interests you, yeah, get in touch for sure.
Cool. Thanks for that, Ryan. Question here on the vector tile generation. And so you mentioned support for PM tiles, and that's what we showed in the demo. But there are other types of vector tile formats like MB tiles. Could you speak about why you're using PM tiles over other vector file formats? I guess that would be a question for
Sure.
James.
Yeah. When I was developing this feature, we were looking at PM tiles, MB tiles, and then MV tiles. MV and MB, not to be confused. So MV tiles is like your standard tile. You can serve MV tiles out of a PM tiles or MB tiles file archive. We looked at that and we actually did implement that originally. The problem with that is every tile is an individual file, and having millions or billions of files, or specifically uploading them to S3, it doesn't go well. If you do the napkin math of the 3,500 or 5,000 puts per second rate limit on S3, it takes quite a while to get a large number of files into S3. We also looked at MB tiles, but the problem with MB tiles is they're SQLite databases. So to query an individual tile out of them, you basically have to download the entire tile archive, which might be several hundred gigabytes. So you wind up needing a piece of middleware. Typically, this is like a tile server. So you have a tile server that's running at all times that has your tile archive downloaded, and it serves the individual tiles out of the MB tiles by running like a SQLite app, like Tile Server GL. PM tiles, like it similar to MB tiles, it is a tile set archive. It contains many tiles or all your tiles. But the way it's structured allows the client, like, for most users, this was probably like your browser, um, to query like the header to get the metadata, which tells it exactly where every tile is in that file, and then use an HTTP range request to request only the bytes that encapsulate the tile that it's looking for. So this means that you can upload a single file to S3. It's quick and performant in that regard. And then your consumer can get access to your tiles without downloading several hundred gigabytes of tiles all at once, and without you having to maintain a tile server that provides access to those. So it's cloud native in this sense. And then I'll add on one last thing here is that the fact that MB tiles or PM tiles is like inherently a single file format presented an interesting challenge for us. We developed a solution here to upload from a distributed environment the single like PM tiles file. So we're able to like continue to like leverage the fact that we have a large cluster here, but still put out that single PM tiles file.
Great. Thanks for that, James. That makes a lot of sense to me. I've got a question here regarding some of the things we showed in the Spatial SQL API. So we showed the example with QGIS. Damien talked about the Airflow provider. We talked about having the Python and Java database drivers. But could we speak about what are some other things we could do with the Spatial SQL API? Like why would I be interested in using that? For example, can I use the Spatial SQL API to move data between systems? So for example, could I write a Python script to export data from PostGIS and load that into Wherobots? How would I know if this is the approach I want to use, or if I want to use the spatial job functionality that Damien talked about earlier? This be a question for Peter. Do you want to address that one?
Sure.
So the main feature for SQL API is to be able to support a Python DB API and Java JDBC drivers. So you can easily connect to Wherobots and use them in your ETLs. We're actually thinking about we already have like an Airflow provider coming with that, at least a SQL operator, and we're looking at potentially using Superset as well. So in case you want to have, just SQL statements and SQL operators running in your ETL jobs, the SQL API is a perfectly nice solution for it. If you want to run your Python code, currently we only offer the jobs API to be able to do that and have something running in a scheduled fashion. We are working on the Airflow Python operator as well. So you can also add the Python code to your ETLs and other jobs. In terms of what you can use it for, you can use it for everything that you can express in SQL or in Python. So moving data, doing all the computations, like basically the API gives you a full range of access to anything that you could potentially do as a SQL statement or as a Python code. That includes moving data. That includes doing all the analytics that you would like to do.
Cool. And a follow-up on that from Amir is asking if we can contribute for more drivers. So I guess there's a couple ways to interpret that. One is, can you contribute more language drivers? So if we wanted like a JavaScript driver or something like that, or also, potentially building on top of the drivers to integrate with other frameworks or systems.
Absolutely.
So I know.
Absolutely. Yes. Let me just very easily answer to that. Absolutely. All of the Python DB API and the Java JDBC driver is out there. We have a GitHub repository available that you can take a look. We already have like integration with, for example, Harlequin, which is a very nice command line SQL interface. And absolutely, please add as many as you want. And if you need anything else and features, come back to us. You can also contribute to the drivers themselves as well. For other languages besides SQL and Python, we are currently not looking, sorry, for Java and Python. We are currently not really looking to add more, but I think we would be open for that as well, especially if there's some good use cases.
Amir, who asked the question, has his hand raised.
Go for it.
Yeah. Hello. The big smile on Peter's face when he said absolutely told me that I can contribute. I was thinking of building a wrapper around the API in PHP. Right now, what I see on the repository, we have Python, we have R. So I'm wondering, what's this? Give us a job or offer us a job from Whereabouts in the future? Thanks.
So good question. We haven't really thought about that yet. I would like to know more. Maybe you should take that offline. And if you can send us a little bit more details on what you're looking for, that would be super helpful.
I would just add to that, we definitely want to support and nurture the open source community as much as possible, especially around Apache Sedona, and especially as we bring these features and functionalities to the cloud. So definitely, we're very much interested in supporting and fostering the open source community and supporting those operations. So yeah, definitely follow up with us either in the Wherobots community, so community.wherobots.com, or if you want to join the Apache Sedona Discord, you can ping us all directly there. Great. Well, I think we are a bit over time here, and I think we got to most of the questions here. I don't see any more hands up. So thanks everyone for joining today. Damien, did you want to close us out with any final last words?
No, that's it. Thanks everyone for joining us today. And you can reach out to us in various forums. We pay attention to there's a support at Wherobots alias, and you can send us a note there.
Great. Thanks, everyone. We're recording, so we'll be sure to share the recording of this on YouTube, and we'll also send out a follow-up email with the link to the recording, slides, and any code that we shared today. And just a reminder that if you want to try out any of the things that we talked about or demonstrated today, you can create a free Wherobots Cloud account and take a look at some of the example tutorial notebooks and get started on your own, working with your own data today. So thanks a lot, everyone, and we'll see you next time. Cheers.
Bye, all. Thanks for coming.